So this is going to be a video just giving you the main ideas that you need to know for chapter 19, which is current of electricity and all the important equations. But you see, chapter 19 is tied to chapter 20 like conjoined twins. Okay, so chapter 19, the circuit is more straightforward. Chapter 20, the circuit is more complicated. Here, we are going to focus on the straightforward circuits that you tend to see in paper 2. Paper 1 ones with the weird bridges and a lot of resistor, that will be in a different recording. So what do you need to know about conductivity or current? Number one, you need to know that current is defined as rate of charge flow. I'm not going to go into detail because it'll be too long, the video, and we're never gonna go home. So I is dq dt, but you know in AS we normally just assume the rate is constant, so can take I is q over t. Reminder, this I unit is ampere. A. This Q unit is coulomb. C. But Q can also be calculated using the number of charges multiplied by the charge of one electron. So this will be number of electron multiplied by the charge of one electron. Don't know why people forget this. So sometimes they will tell you, calculate the number of electron passing through point A on the circuit in 20 seconds. Then student don't know how to calculate it. You just divide by the electronic charge. Okay? So sometimes they can ask you this question. You go and look at past year. This one, they can ask you quantize. What is means by quantize? Okay, so this means that Q must be in multiples, integer multiples of E. This is what quantize means, just a definition. Right, number two. Actually, normally when I think about circuit, right, I think about my good old V equal IR. One equation to rule them all. So now I need to talk about V. What is V? V is potential difference. But V also has a different alter ego. Potential difference versus EMF, electromotive force. Okay, so they have the same unit. The unit is still volt. So this means they have to have some common things, right? Because they share the same unit ma. So they should describe similar things. Potential difference and EMF, they are both work done per unit charge. Okay, but specifically, potential difference is work done. This one is outside the circuit one. So work done in converting outside the circuit electrical energy to non-electrical energy per unit charge between 2 points or across a component in a circuit. Can be component, can be components. This is potential difference. So what we're trying to say is outside the circuit, the energy conversion is electrical to non-electrical. Maybe, let's say you have this one here, okay, and you have your resistor. Maybe you got two resistor lah. I don't know lah. Why is this one is 2R? Doesn't matter. Maybe this is your point A and maybe this is your point B. So when you want to think about the potential difference of AB, this resistor will get hot, right? It will get hot. So your electrical energy converting to non-electrical energy per unit charge is here. Please remember the per unit charge. People always forget. All right. So this is potential difference. What about EMF? I'm going to copy the sentence. EMF here is the work done in converting non-electrical energy to electrical energy per unit charge, not between 2 points. So this one can be inside a cell or a power supply. Okay, so your non-electrical energy can be chemical energy, can be, depending on your cell, can be solar energy or photo energy because you are using a solar cell. So the key point here is non-electrical to electrical, and then the other one is electrical to non-electrical per unit charge. Okay, that's it. Got equation. V equal IR lor. Okay, number 3. The third main character, resistance, R. R has 2 forms of equation. R can be written as the ratio of V over I. So this R is V over I. Ohm's law. Okay. But if let's say you want to state Ohm's law, your statement is V is proportional to I. Not the same thing. This one is for any component. Because you need to think about your IR, VR, VR, VI, IV. What talking about? IV characteristic graph. So your IV characteristic graph got a few pattern, right? I'm just going to draw the positive side, okay? You want to see the one with all 4 quadrants, one refer to the notes. So if let's say I draw the IV characteristic graph, I have one which is straight line. So this will obey my Ohm's law. So normally this is metallic conductor at constant temperature. Normally the wires we give you in the lab and you do the experiment quickly. The other one, the gradient increase one. So the gradient increase means resistance drop. The hotter it is, the smaller the resistance. Because the larger the current, the smaller the resistance. When I increase, R decrease. This one is normally thermistor. Because thermistor is made out of semiconductor, the electron very lazy, don't want to move. You heat it up, you give it more current, it is more incentivized to move. Filament lamp, like that one. Current increase, gradient decrease, so resistance increase. This one is your filament lamp. You put more current or there is more energy loss, so the resistance increase. So make sure you know the IV characteristic graph and how to read them. Okay. Part 4. Okay, side tangent. Auxiliary equation about dimensions of your conductor. The first one is current. Current can also take the equation. This is definition, but I is also equal to NAVE, N-A-V-E, N-A-V-Q. So please know that this one is your number density or the number of electrons per unit volume. A is the area of wire. Okay, the surface area of wire. I think the rest is self-explanatory, but I will draw for you. So let's say this is your wire. And maybe you have a current flowing through the wire I. So this is your A. Okay. And inside, if the current is flowing in this direction, then the electron will backflow in this direction, right? So this is V. This V is known as drift velocity. Very important. You have seen drift velocity many times, MCQ, structure, they can ask for ratio. Okay, so this is one question where they can ask for ratio. Second one that is dimension related is resistance. Once again, I present to you a wire. If I want to find the resistance of this wire, R is rho L over A. A is once again the surface area A. L is the length of the wire. Rho is resistivity. Resistivity is depend on material. Constant wire will have different resistivity. If they say two wires of the same material but different diameter, then you just treat resistivity as constant. Okay? For this one, drift velocity, this number density is also constant for same material. So the material matters. Okay? This one is chemistry ma. Certain material, the valence electron got more energy, then it will move faster. Or certain material, valence electron, less energy, doesn't move. Okay? So just understand for physics, what we need to know is that it is dependent on the material. So the two equations that I have written that is related to the dimensions of the material, normally they will ask ratio, either in MCQ or paper 2. Okay. The other questions like graph can be asked in MCQ, so you need to know how to graph, but you also need to know how to interpret the graph. Okay. So let me just suggest some questions to try if you like. I don't know how the question look like, Mish. I long time never do. My brain is filled with other chapters. I only studied chemistry last week. It feels like hydrocarbon haven't left my brain. Okay, you chill first. Technically, your brain is made out of hydrocarbons, so that is okay. So for the IV characteristic graphs, you should try ON19 if you haven't tried lah. Okay, if you try already, then you just, I don't know, do something else. Or N19, and I kind of want you to try the other one that has this one. I'm pretty sure I discussed this in class already, but it's probably time to do a bit of revision or pretend you haven't do the question yet. Okay. Right. So this two is enough for the IV characteristic. For resistivity equation. Actually, resistivity a bit hard to find. Got actually. This one actually got include resistivity as well. But let me try to see if I can find another one for you. So basically, if you don't know this, go do more question. If you know this, you are sure, then it's okay to, for now, not do anything. Okay lah, 3 is more than enough. Haven't do anything yet, then go do. I see a lot of ratio for average drift speed. So many. So then I guess the ratio for resistance is a bit sideline. Got lah, this one. You can try ON17 paper 2-1. Good enough. Okay, try this for these two part. This one, we wait until Kirchhoff law. You will see them again. For these number density ones, there are quite a few. I think I'll just suggest one for you lah. This one or two. This number density drift velocity one, you can try. ON17 paper 2 question 6. If you haven't tried. And yeah, I feel that this one set in your test before. I could be wrong. I don't remember. I think this one I have chosen for your test, or Mr. Chan has chosen for your test. And you do look at it lor. If you know how to do, you do before, then just skip lah. If you don't know or you feel that you haven't tried that question before, then do lor. Okay, and I'm gonna just pick another one. May, June 17, paper 2-1, question 6. Okay. These are the drift velocity questions. Okay, so what else do we need? I think, last one, power. Power. Do we need to know how to derive? Sure, we can. Energy per unit time. So, energy, potential difference is work done per unit charge, correct? So, energy is charge times potential difference divide by time. What is Q over T? I law, I times V. I power is equal to VI. This is a super simplified derivation, okay? Actually got some calculus one, but never mind now. We just pretend the calculus is not there. You can use V equal to IR to do some very quick conversion. No need crafting table. This one can be I square R. This one can also be V square over R. More important is to know when to use what equation. And the solution to that is read the question, figure out what information you don't have, and then use them. Okay. All right, so that's the what you need to know. Just 4 stuff. What is current? What is potential difference? Because there's potential difference, immediately if I see work done per unit charge, I immediately would think about power already. You know the difference in definition between PD and EMF, okay? Resistance, IV characteristic graph, try this. Then think about the ratio question. Can ask about resistivity, focus on resistivity. Can ask questions, focus on drift velocities, which are this one. Go and try them. I'm going to focus on the ON20 papers, so hopefully you have tried them. Pause the video, log off the meeting, later come back again. No. Okay, anyway, let me crop the question. Mana dia itu? Okay, paper 2-1. ON20, paper 2-1. We'll do both questions and then this paper is a slight bit anomalous, but no worries. Easy circuit, no complicated stuff. Just 1 or 2 resistors, just chilling there. No big deal, just minding its own business. Trust yourself. Okay, so let's start from the top. Define the ohm. Sounds like a brand, but to define the ohm is a unit. If ohm is a unit, we will use unit to define units. Okay, so R is V over I. So ohm is a volt per ampere. Volt per ampere. 1 mark. Okay, that's all. No more now. If they ask you to define resistance, that is potential difference, ratio of potential difference to current. So if they ask for resistance, you will put something like ratio of potential difference across the component, because you're finding the resistance of the component, to current flowing through the component. Okay, anyway, our component here is a uniform wire. Got resistance already. They give length. They give resistivity. Wow, so sneaky. There's a prefix hiding here. Ooh, 18-year-old me may forget the prefix. Okay, until the cross-sectional wire of area of the wire doesn't make sense. So if got R, got L, got rho, of course we're going to use R is rho L over A. Wow, 3 marks. Nice bonus. Thanks, CIE. Nano is 10 to the power of -9. You want to know something? We have to test your prefixes in the paper. So it's either we test it indirectly like this or we test it in question 1. So just look out for prefix, okay? We have L, 2.5. We're looking for A, right? Right, this is A. Okay, hang on. Let me write this properly so that my teacher will not grumble. And by teacher, meaning I don't write my answers horizontally. Okay I got this one already. I press calculator. Wow, so easy. Are they going to smack me later with a difficult question? Don't know. But if they give 3 mark, I take. Making sure I convert all the prefix. I got 3.6 times 10 to the power -7 meters squared. Makes sense because wires are not supposed to be thick. And we -7 meters square. You can write 3.59, but 3.6 is good enough. Okay. Next, a cell of EMF E and internal resistance R is connected to a variable resistor. The current in the circuit is I. State in terms of energy. Okay, so you must use energy, energy, energy. Why the potential difference across the variable resistor is less than the EMF of the cell. Whenever they say why, you must give a reason. I feel I'm teaching you how to write essays now. But in one sentence, because it's 1 mark. So the reason why the EMF, so EMF, right? Let's say, for example, this EMF is 12 volt. Whenever you see 12 volt, the battery, from the battery or the cell perspective, it will convert 12 joule of non-electrical energy, maybe chemical energy, to electrical energy per coulomb. Let's say I put a voltmeter here, and this voltmeter only 10 volt. Then the battery is like, hey, I give you 12 joule leh. Why you only convert 10 joule of this electrical energy to non-electrical energy, for example, heat? Where did the other 2 joule go? Then the internal resistance is like, hey, sorry, bro, I need to take some lah. I need to take some because we need energy to convert energy. You need energy to chew your food. Okay, we need energy to convert energy. So you just mentioned there is lost volts, missing volts. Why? Why? Due to internal resistor of cell R. Okay, don't just say lost volt. Say that it's due to internal resistor B1. So this is why the potential difference of the resistor, let's say 10 volt, is less than this 12 volt. Okay. But when they say lost volts, did we talk about energy? They say in the perspective of energy. So do you think we can get marks? Remember, Cambridge is sneaky, but you are more sneaky, or maybe you are more veteran now and they can't pull the sneak on you. This one will not get you marks. Normally it will, but now they say energy. No marks. How do you need to talk about energy? Instead of lost volts, you can say there is energy dissipated as heat in the internal resistor R. So a lot of times people memorize the first sentence lah, okay? But I want you to understand that this lost volt translates itself as energy dissipated as heat in the internal resistor. This one is your B1. So this one is wrong, not because the statement is wrong, but we didn't include energy in your explanation. All right, state the expression of EMF E in terms of I, R, and R. So remember I said one equation to rule them all? Think of the perspective of the current. The current that comes out from this circuit will pass through this resistor R and then pass through this other resistor R. So the total resistance, this two is in series, right? So if you use V is equal to IR, your E is actually equal to I, R plus R. All right, so the actual potential difference is 12. And 12 is used inside and outside. 10 plus 2 is 12. There, I times R is 10, I times small r is 2. Okay, just state only. Okay, lor, I, R plus R. Yay. Next. The resistance of the variable resistor is changed so that it is equal to R. Okay. R equal R. Determine an expression in terms of only E and R for the power P to be dissipated. Okay, so now I need to think a bit. P is equal to, you can use VI, you can use I square R, you can use V square over R. But they only want E and R, but they also want the variable resistor. Yeah, okay, you wait. Let's think about this. I want my P to be equal to something E something R. And then I stare at all these equations. I need to find a way to introduce R. Means I can introduce small r because big R external resistor is equal to small r internal resistance. Great. So now we need to substitute either V or I. Okay. And we need to bring in E. And they asked me to write this equation. So probably I need to use this, right? All valid points. Okay. So also E is equal to I R plus R. So I'm going to substitute my I as E over R plus R. If you watch the video where I derive the maximum power, these are the steps. But you don't watch, then it's okay, it's okay. Our point is I want to be able to substitute away I and probably R. So I'm going to use this equation. Because I don't know the EMF. I mean, I don't know the power dissipated in the variable resistor. Must be variable resistor. So if you think about this thing, like that, this variable resistor is R. So this power dissipated, let's say this is VR, you have to use VR. Okay? If you want to find the power by the battery, then you will use EMF. P is equal to EI if it is power supplied by battery or by the cell. That's why we use this one. We're going to use this. Okay, so P is equal to I square R. So power is equal to E over R plus R whole thing square times R. So we will get P is equal to, oh, wait. We also know R is equal to R. Oh, can substitute. E square R over R plus R. Is it R plus R? I square R. Did I do it? Oh, no. We need to square this one also. Correct? Yeah, correct. Now. Okay, so now P will be equal to E square R over R plus R is 2R. 2R square is 4R square. So you can cancel one of the R. You will get E square over 4R. Okay, do slowly. R plus R square. Okay, so what I did was I substituted I. This I substituted E is R plus R, and then I square, and I multiply lah. But also at the same time, R is equal to R. So all these R's, R is equal to R, I substitute. This R also I substitute. So now it looks like this and this. Then I simplify. E squared times R is on top. Okay. Then down here, R plus R is 2R. 2R squared is 4R squared. One of the R can cancel off. You get E squared over 4R. Wow, I missed this one 2 mark. Yeah, not every mark is the same. But the 3 mark was easier. I know. There. Not every mark is the same. Okay, where do you get marks? You write a right power equation, you get C1. But has to be this one. Other power equation is not accepted. Okay. And then you have substitution, correct substitution leading to this answer is C1 mark. So generally, if you substitute I correctly, then you get C1. And then leading to this answer, substitute I, and then leading to this answer is A1. Okay. So E squared over 4R. That is variant 2.1. Let's look at variant 2.2. That'll be the last question of the day. I'm going to keep this here for 2 and check the chat. Okay, if we didn't write heat, but energy loss due to internal resistance in the cell, that is okay. Chat, that is okay. Okay, if we don't write heat, just mention energy loss instead of lost volt. I know it's very frustrating because Miss, volt is energy per unit charge. So got lost volt, then my got lost energy. No, I know. But if they ask for energy and you write energy, your marks will not be deducted. If they ask for energy and you write volt, you don't have a chance to argue with them. So just write what they want so you get the marks that you want. Write what they want to get the marks that you want. Okay? Okay, I'm gonna last one. 20 paper 2 question 6. By the way, guys, variant 2-3 was your class test. Okay, so because variant 2-3 is your class test, you if you don't know, you just go and do again lah. Okay. If you still don't know, then come ask me lah. Class test, bro. What else? Here. Why did I crop so big? I should make it smaller. Oh, this question feels a bit different than the other variant. Can do one. Just gotta trust yourself. And also quite long. Okay, let's go. Question 6. We check the chat. Or rather, who is? Okay, never mind. Okay, let's continue with the last one. Derivation. This one, I'll talk about the derivation during the next time we talk about circuits, but basic stuff I'll tell you lah. So if they label everything for you, then the derivation is simple already. Please follow their labeling, don't come up with your own labeling. Show that the combined resistance of the network is given by this one. So when current is in parallel, right, think of your Kirchhoff first law. Current going in, which is the yellow current, is equal to the sum of the current going out. So some will go here, some will travel here and go here. Some will travel here and go here. Hiya, your exam also can Kirchhoff law ma. Room 303, 304, which can get very hot. There are 2 doors, right? Come on. How many times you were waiting there for them to collect your paper and then you were just contemplating life, your life decisions while waiting to be released from the exam hall? So number of students that exit here and the number of students that exit here, and let's say Miss Lee stand here to count student, the corridor is here. The number of students that come out from door 2 I2 plus the number of students that come out from door 1 I1 must be equal to the total number of students that come out here, I3. I3 is I2 plus I1. It is called logic. It is called conservation of things. If I have 40 students exiting the back door and 45 students exiting the front door, I wouldn't suddenly have 90 students because where did the 5 students come from and were they hiding under the table? Because I didn't take their attendance. Okay. All right. So here, what am I talking about? We want to show the current, so I can write the equation. You write the equation because I don't know what to write, but you can write equation. Please don't leave blank, this kind of thing. I1 plus I2 plus I3. Well done, you get 1 mark. Liao. Don't know what I'm doing here, but I got a mark. Yay, B1. Okay, what else? By right, the resistance and R1 and I1, you multiply together will be equal to V. So the potential difference are all the same because these 3 things are parallel. Okay, whenever the current splits, it is parallel. So I will just make a statement like the potential difference across R1, R2, R3 are equal because you are talking about parallel connection. And I will just say equal and I put equal to V lah. Okay, we are ready. You start from this equation. I is equal to I1 plus I2 plus I3. Then you think to yourself, V equal to IR, an equation to rule them all. So we can write I is equal to V over R. Of course, again, what are we trying? What is our goal? Our goal is to only leave R behind. Everything else have to go. Only R. So this I will be equal to V over R because this is total current. This I is the total current. Then split into 3 ma. So this is total voltage. Same. Okay, so this is V over R1 plus V over R2 plus V over R3. But all the V can cancel because they are the same. So hence, 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So if I see this working and you cancel off the V, this is the key step, your B1. Okay, that is all. Next. EMF 8 volt, internal resistor R1, 2, 3, don't panic, only 3. Okay, resistor Y has a resistance of 16 ohm. You got the current. Okay, sure. Calculate the current in the battery. Easy. So the current that come out from here will split into 2. Some will go here and then go home. Some will go here, go down here, go up, and then go home. Please note that the internal resistance receives both current, and the total current inside the battery is actually the sum of 0.49 and 0.45. Okay, so they both pass through. It's a common highway. Okay, 0.45 plus 0.49. This will be 0.94 ampere. I wish to casually remind you for the 372 times, all this answer is 2 to 3 SF. Okay? I don't care if it's a perfect number. This one, of course, can lah, but I'm just saying in case you get a nice number like 1 ampere. Internal resistance of the battery. Okay, can. Let's calculate. One equation to rule them all. V equal IR. I'm going to find Vy because I know the current and I know the resistance. 0.45 times 16. 7.2 volt. Okay. So if the potential difference across here is 7.2 volt, it is connected parallel to this one. So generally the way circuit works is that whatever you connect, whatever is connected between these 2 points, so you can, these 2 red points, I call this AB lah. Whatever you connect between AB, you can connect a resistor X and Z, you can connect resistor Y, you can connect something else. The potential across AB must always be the same. This is the benefit of parallel circuit. So if let's say I put a power supply here, internal resistance also if you want, I can put, okay, let's assume the power supply is perfect. Perfect 12 volt. Perfect 12 volt. I put a lamp here. This lamp is going to get 12 volt. I feel the lamp is very lonely. I include another resistor here. This resistor going to get 12 volt. Then I feel that I need to bring a threesome to the party. I'm going to put another lamp here, different color one. Color lamp also 12 volt. I go and put another resistor here, also 12 volt. I think you get the idea already. But miss, how so many energy? This battery will deplete faster, or aka die faster. The more things you connect, die faster. Think of your connection, your 3-point part. I'm pointing at my extension cable here. All the extension cable, whenever you plug something in, is like this one. Your computer, you charge your phone, charge your laptop, charge your iPad, put your Nintendo Wii, you charge like that, then the power supply will deplete faster, electric bill very high. Okay? So your Vy is 7.2. And if we think about the 7.2 here, why I do this to myself? Okay, this is Vy. So if this is 7.2 and the total energy that we supply is 8, the lost volts is 0.8. 0.8 volt is the missing volt. So if you are asked to find the internal resistance, so hence the lost volt will be equal to 8.0 minus 7.2. And then you can use V equal to IR, again, one equation to rule them all. 8.0 minus 7.2 is equal to the total current we have already, right? 0.94 times R. So that way, your R would be 0.85. There are many ways to write the equation. Some people prefer to finish everything one go. So they may say, Miss, can I use this equation? Can. But the problem is you don't know the internal resistance. Never mind lah, Miss, I can modify. This IR is actually V. Then I plus IR. I know this is 8. I know this is 0.45 times 16 plus IR. So I end up with 8 minus 7.2 is equal to IR. See this? It's the same. So 0.8 will be equal to 0.94 times R. I can find R. Up to you lah. Some people like to step by step. Some people like to hampalang. All one go. Some people bake cupcakes. Some people fry rice. I don't know. My analogy is not working. I'm hungry. Okay, next. Which one? Which step? The step here is when I see this 8.0 minus 7.2 or 8.0 minus 0.45 times 16. So this is your C1. This is your C1 equal to IR law, of course, leading to the final answer A1. Of course, if I do as a student, I only want to pick up my calculator one time. So I will do this method. I'll leave this as alternative method. As usual, you know where to find your notes. And I'll just put this here. Okay. I'm gonna move on. Let's see after I successfully rearrange this thing. Okay, can now. Okay, leading to the answer 0.85. Okay, resistor X and Y are made from wires of the same material. Okay, so same row and cross-sectional area, same area. The average drift speed of free electron in X, Vx is this one. Calculate the drift speed of the free electrons in Y. Okay, to find that, I'm just gonna take the circuit because I don't want to scroll. And I'll just put it here. Okay, this is your circuit, huh? Okay, let's think a bit. This is our circuit, and I want to find between X and Y. So I know the current. I think which equation should immediately come to mind is I is equal to NAVE. Identify the constants. Same material, not rho, N and rho is the same. So this was what I mean just now in the summary where I say, oh, when they say same material, why is it important? Because not just the resistivity, number density also the same. So this is constant. Same cross-sectional area. This is constant. Electric, E is always constant. So from here, I can get I is proportional to drift velocity. Very nice. So I will say the current in resistor X divided by the current in resistor Y will be equal to the drift velocity in resistor X over the drift velocity in resistor Y. Current in X is 0.49. Current in Y is 0.45. Drift velocity in X is 2.1 times 10 to the power negative 4. Then you want to find Vy. Easy. Very easy. 2.1 times 0.45 divided by 0.49. this will be 1.928, 1.93 times 10 to the power negative 4. You can write 3 SF, you can write 2 SF, up to you. Okay, so this is what I mean by sure we'll use ratio 1, either in MCQ or paper 2. All right, resistor Z is replaced by new resistor or smaller resistance. Haha. State and explain. The dreaded state and explain. The effect, if any, on the terminal potential difference of the battery. Okay, I'm going to steal this again, just bring it here so I can stare at it. Our terminal potential just now was 7.2, right? U is 7.2 volt. U is 7.2 volt. U was 0.8 volt. Goodness, 0.8 volt. Will this terminal potential difference change if Z has smaller resistance, RZ decrease? Everything else is the same. So the so-called terminal potential difference is the potential difference, just now I label AB, right? VAB is your terminal PD. Okay, so to decide your terminal PD, is actually how much current is flowing through the battery. If you got more current flowing through the battery, then there's more conversion here. There's more conversion, then we need more energy. So generally, if let's say this is I, if I increase, there's more lost volts. General term, more lost volts. Terminal PD drop. This one is general. Let's say you totally cannot your brain freeze now, or suddenly the invigilator say, candidates, put down the time is up. You don't know what to think already. You faster write this one. There is more lost votes. There is less lost votes. Just write something. Just write something. More lost, less lost, whatever. If you got time to think, that would be great. Okay. So think along these lines. Is there more lost votes? Is there more less lost votes? So we need to decide whether the current increase or decrease. How do we know whether the current increase or decrease? Check the RZ. If your RZ is bigger, means you got more loss, more decrease, smaller resistance. Then what happened to your total resistance? You might be thinking, Miss, it's impossible to tell because number one, I got no numbers on purpose. One. Number two, I parallel, I don't know. Okay, you chill first. You think about this 0.49. If this branch has less resistance, because just looking at this branch, right, this X and Z in series, you will have less resistance when RZ decreases. So when this resistance is less, then the total resistance will be less because of, okay, let's give some number. Let's say this is 16 and this is, you put number. Let's say this is 16, this is 8, and this is, they are not real numbers. I can calculate. I guess, I'll calculate for you. One equation to rule them all. 7.2 is 0.49 times R, X, and Z. 7.2 divided by 0.49 is 14.7. So the resistance of XZ will be 14.7 ohm. So if resistance for Z decrease, can I say the resistance for XZ will decrease? Because X and Z in series, you just take Rx plus Rz. Okay, how to find effective resistance or total resistance? You will take 1 over resistance of XZ plus 1 over resistance of Y. Whole thing inverse. So what you're going to do is you're going to take 1 over 14.7, but now this one is less. We compare. Plus 1 over 16 inverted. You are not convinced? You got time? You can calculate. You no time? Then have to develop a sense of Because for me, I know the resistance decrease, but do you know? I don't know. Resistance will decrease. The total resistance will decrease. But here is me trying to prove to you in your brain why it indeed decreases. So this answer would be 7.66 ohm. RZ decrease. Yeah. Let's say we put R exact as 10 ohm lah. Put any number you like. Decrease can now. Then this one will be 1 over 10 plus 1 over 16 inverted. So let me put this in. 1 over 10 plus 1 over 16. This one will be 6.15. I got explained before why I write the power -1 big because I am also that student who forget to inverse my answer. So here is how I generally learn one. I do a test, I think I did very well, and then when I get back the paper, I see all my careless mistake all over the place. So after feeling sad for myself for 2 minutes, I take out a different color pen and modify my working so that even if I'm tired and sleep deprived, such things will be minimized. So there's a strategy. I share my strategy with you, but it's also very personal and dependent one. So I write like that so I remember to inverse law. So this is 6.15. Can you see? Total resistance decrease. Okay, so whenever you are summing parallel resistance, right? The resistance and also the total resistance for parallel connection is always smaller than the smallest resistance. What's the smallest resistance between these two numbers? 14.7. 7.66 is smaller than 14.7. 6.15 is smaller than 10. It must be smaller than the smallest resistance. You don't believe, you go and try, no? Or if you're good in maths, you see the number, you also know already. So no matter how many resistor I add, 1 over R1, 1 over R2, 1 over R3 is equal to 1 over R. R is always smaller than R1, R2, and R3. Smaller than the smallest R. So if I decrease this R, this one will decrease one. Okay, so R exact in decrease. So R total decrease. This is what we want. Total resistance decrease. So when total resistance decrease, current increases, more lost volt, terminal potential decreases. Okay, so we go. Must have the word total, total or combined resistance of the circuit decreases. So because of this, current in the cell or in the battery increases. More lost volts. So terminal PD decreases. Total resistance of the current decreases is B1. Okay. Terminal PD decreases is B1. I write the middle sentence as a connecting sentence because that is the idea flow in your head. This entire thing is the idea flow. This whole thing. Okay. You don't have to, if you just look at the mark scheme, right, it always feels like their points are very disconnected. That is because they are not explaining things to you. They are telling the examiner, if the student write these keywords, give them marks. That is the purpose of the mark scheme. But the thought process is when you decrease the resistance of a branch of the resistor, the total resistance will drop. Okay, you're only as strong as your weakest link. Your resistance is only as large as your smallest resistor. So if the resistance drop, the total resistance drop, then the current increase, there's more lost volts. Will there be mark here? Maybe if this is 3, I don't know, just write lah. Current in battery increase, there's more lost volts. It fits in your head, right? And because of this, the terminal PD will decrease. If after you write this already, you feel you don't trust yourself, got trust issue, it's okay, I got you. Please make sure you got extra time and then you just do all this calculation on your exam paper lah. Normally, normally in circuits, normally, you have margin, you have spaces in the margin one. Just go do lor, go try. Okay, so this is the circuit, basic circuits. Okay, so make sure you know the 4 important ideas: current, potential difference, EMF, resistance, IV characteristic graph, and the ratio type of equation where it's related to dimensions. And I've also suggested some questions to try. I will include the printout inside the Google Drive folder. Okay, all right, that's it for this chapter 19. We'll do 20. Oh no, before I go, tell the people how many marks is this thing. Okay. I think I'm a bit losing my mind. Okay, chapter 19, you will expect 2 to 3 MCQ plus 1 structure. So I'm ballpark. My ballpark for chapter 19 is about 12 to 15 marks. 12 to 15 marks, guys. Chapter 19, 12 to 15 marks. You have to know. If you don't know the complicated circuit, you maybe lose 3, 4, 5 marks. Maybe you don't know how to explain stuff. Okay lah, maybe you lose 2, 3 marks here. But this is important and most of it is easy. 12 to 15 marks. Because normally one structure is about 8 to 9 marks ma. Okay. Chapter 20 is where you get the complicated circuits one. So those is maybe about 8 marks. If you include chapter 20, then the whole thing will be about 20 to 25 marks. So chapter 20 is maybe another 8 to 10 marks. But not more than 8 lah. Generally, it's about 8 marks. Because the main idea here forms the foundation for chapter 20. You don't know 19, you cannot do 21. Would you agree? 20 is where we bring in all the complicated bridges. Whereas for now, trust that you will definitely see a structure or at least 75% of a structure question. And maybe after that, they go and connect some weird bridge there. Like, okay, lah, sure. Take my 4 mark, take my 3 mark if I cannot do. But the remaining 7 marks can do. Okay, so generally looking at about 12 to 15, maybe a bit more, depending whether they ask more waves or more kinematics or more electricity. But around there lah. Okay, that's it for chapter 19.